All right. So the first thing I want to show you is this. Doesn't work. Uh, is this poster, and this poster is kind of a summary of things that I will discuss more in the Blackboard again because I want to talk more about concepts. So the first the first idea is that you have an experiment, a conventional experiment like Next or like Nexo, in which you have the techniques that we have already discussed, right? And now, as you have seen, the need to reduce, so 10 to the 27 years sensitivity means somehow one background event in the region of interest per year. Now this is difficult, but maybe can be done. 10 to the 28 means a fraction of an event, 0.1 event, which means in practice zero event. This is difficult for two reasons. Because in a way, you need zero background, and also because you need to guarantee that you have zero background. So you need to have something extra in hand that allows you to be sure that you have zero background. Now, the point here, we will come back to this thing later, but the point here, there was some place here we could, let me see. Okay, so one way one way to be sure if you have a neutrino double beta decay, whether with two electrons or without two electrons, you're going to have a barium atom. Actually, barium is such that it will immediately ionize because it's not a noble gas anymore, right? And so it has two electrons. It has two extra charges. It will immediately transform itself in a Va++. Why? Because you're going from zero to cesium and zero to barium. You're dropping two charges, and then there are two extra electrons, which in the last, so it will kick them out. So what we are doing in Next, or in EXO, is to look at these two electrons, remember. And looking at these two electrons, let's look a little bit at the way we do it in Next. So we have the gas detector. Let's imagine that we have an interaction here. And so I have my electron here. And so I have my little electron here. I have the drift. I have my signal. All right? At the same time, here, in this precise point in which I am producing the two electrons, I am producing a doubly charged barium ion. So the barium ion will slowly go in this direction towards the cathode. Correct? Now, the barium ion moves faster or slower than the electrons? Way slower. 10 times slower. So my electrons arrive here when the guy is still thinking I should go. All right? My electrons arrive here, and then I go through my usual analysis. They will arrive here after what? They go about 1 millimeter per microsecond. So very quickly, in a millisecond, at most, I will have a signal. So in that millisecond, I will immediately measure the energy. So remember, 0.5 MeV, maybe I have a signal here. Interesting. I will see the two electrons. Actually, I will program a neural network in a chip so that it will be pre-programmed in a chip to immediately say, boom, two electrons. Okay? And then it will tell me, yes, two electrons. If these two conditions, if any of these conditions is not achieved, something here or not two electrons, go to hell. Not interested. If I have this condition, to write the energy to electrons, then I am in the condition in which my experiment, remember we have been doing the college, which I should have very few events like this. But it could be a background. Well, this will happen after 1 millisecond. Yes? So I have plenty of time to say, okay, if this is true, sometime later, many milliseconds later, a barium ion is going to show up here. I know exactly when, because I also have the position of the interaction. So I know also exactly when I can open an electrostatic gate and let the barium 2+ ion come in. Otherwise, my electrostatic gate is closed and you cannot get in. All right, so because I heard this, ping, then I open a gate here. You can pass. And the barium ion passes. Now, I need a magic way to grab this single ion and to see that this single ion is in the object that has grabbed it. But the first thing that I want you to understand is that if I manage to find this ion, then I have something incredibly powerful, which is what we call a delayed coincidence. It is delayed because it happens a while later, but it is a coincidence. I see something which has the right energy, it has two electrons, and then it has a barium 2+ ion. Who can fake this? Nobody. You mean other barium 2+ metals there? It will go to the wall? Well, yes, no. I mean, the barium ion is driven by the electric field. There is an electric field here. And the electric field makes you drift. Of course, if you don't put an electric field, the guy goes, but there is an electric field. It's a flow, it's a river. I am putting you 400 volts per centimeter. I'm not letting you go nowhere. No way. This electric field is it's completely composed to drive the electrons and the barium exactly through the lines of change. It has no. I mean, if it is here in the very borders, maybe. So some of the events here, these events here, I will throw them away anyway. Remember that when we do this experiment, the first thing that we do, even in gas, not to mention in liquid, you have the detector, and the first thing you beat to a region around the walls and the cathode and everything. So what you say, this guy going here could go, but not here. The guy goes like hell, right, straight. Okay? Actually, the question is a good one. What happens to this barium? It's a single ion. The guy actually will grab a few xenon atoms as travel companions. And they will go there making a snowball. Typically, up to 10, we've done the simulations and the analytical calculations for that with the theorists. We have published a very nice paper on that. And actually, rather than having a single barium ion like there, you have this super ball running, and the barium 2+ is surrounded by positive signion ions. But they are very weakly bounded. So when they find some other electrostatic interaction which is stronger, it gets rid of them. Okay? So the barium ion will go, and we have computed actually what is the lifetime of this barium ion. So how often it will go, and it's essentially 100% of the time. So this part of the problem, which was not obvious, seems to be relatively simple. The efficiency to transport this guy to here is good. Okay? So you could tell me, maybe there is barium 2 plus ions in your detector that are ejected by the metallic grids. Or what? Who knows? Maybe not barium 2 plus, but sodium 2 plus or other metals that could fix you. Sure. But the problem is that what you're not going to get is in the exact millisecond in which I open the window and I say, no, you can pass, now you cannot pass. Something can produce barium 2 plus, but not radioactivity. Radioactivity can produce 2 electrons, but not barium 2 plus. So the only way you're going to have barium 2 plus and 2 electrons is if you have a double beta decay. Actually, xenon 137, which is such a nasty decay, will not produce, it's a beta decay to xenon 136, so it will not produce barium plus. Okay, so now we have invented something interesting, the delayed coincidence. And this is the power of it. Sometimes when people talk about barium tagging, you tend to think that what is powerful is you can see the barium. Sure it is. But the argument, if you manage to do that, the argument will be, oh, well, how do you know? This is not spurious. Because it needs to happen in coincidence. Okay? And that is actually the way the neutrino was detected by the first time. So you had all the reactions in these nuclear reactors, right? And then what happens is that the neutrino kicks a neutron out. So you first detect the first signal, and then the neutron works around and it annihilates. And you have boom, boom. And this coincidence cannot be faked by backgrounds, or it's very strangely faked by backgrounds. Okay, so now, second problem. I need to grab the barium ion. How do I do that? Okay, we can think of a number of ways, but one interesting way is maybe I made a net, a fishing net. So I put a fishing net here. The barium moves here, zip, or zip. What is this fishing net? The fishing net is done taking a layer, planting molecules into some suitable layer. This suitable layer may be made maybe of quartz or ITO. These molecules contain an element here, which is something that allows me to attach this group to this metal. Okay? And then they have something which will capture the barium. And then they have to be designed in such a way that they can give you a signal when you capture the barium. And there is around somebody who is here trying to look unconspicuous, who would volunteer to a gong show very gladly, because he's a chemist and he's, works on this kind of stuff. And he can give you some more details on how these molecules are made. These molecules are very pretty. I'll briefly show something later. But these molecules are wonders, right? They have something called an azacrown thing. I learned all these things. You need to learn a new language with these chemists. They don't even talk like normal people. And, they They talk in very, very long terms, like as a crown, be the bed. It's impossible to talk to them, but with some passion you can. The Ether crown is a crown. It's literally a crown. It will grab the metal. The metal will be hanging there in between the nitrogens. So this is something that they know how to do, and it is achieved. This is not a problem. We know how to do that. We have done this already. Furthermore, once you grab the monster, the molecule does something like this. And then it changes the chemical properties of the molecule, and it changes its properties. In which way? In the following way. There are many ways around, but I'll give you one which is particularly pretty. The free molecule, if you excite this molecule with a laser, say a laser in 400 or whatever, it will answer back with some radiation. It will give you some color, maybe. I will give you whatever, depends of the family of molecules. These guys produce one family of molecule after the other, right? But typically, maybe the molecule will give you some red signal when you excite it in some blue. You go with the laser, you excite it, and then it gives you back red signal. Now, when the molecule grabs the barium ion, it changes its properties, okay? And the result is that it shifts towards the blue. So now you have two colors, free and chelated. Okay? Now, suppose that you have this situation, which actually our team in Donosti is able to do this not only with two colors, but with two different families in different colors. Now, the problem that you have now is try to separate these colors as much as possible. If these colors were sufficiently separated, I can now put a filter here and say, okay, this is chelated, period. If the colors are not that well separated, then of course you need to pay, you have a tail and you need to separate the tail from the signal. So you're back again on how to separate the signal from the background. The other thing, the other problem that you have is that you want to separate single molecule. You want to be sure that you are seeing a single molecule, right? Because consider this. Suppose the situation in which my chelated molecule shines here, okay? And the free molecule shines far away, but there is a very, very tiny tail that comes in, right? But of course, I am making a layer of molecules, and this is all full of molecules, right? One of them is free, is chelated. The other ones are all free. But when I excite with my laser, what am I doing? My laser has typically a spot of about 1 micron square. But 1 micron square is a lot of molecules. Depending on my layer, I can have 10,000 or 100,000 or 1,000,000. So all of a sudden, I am putting the spot here, right? And I have a signal from this one, but I have tiny signals from all of them. And a tiny signal from 1,000,000 of molecules could be complicating my life. Here it comes, the next step. But what if I insist that you are a single molecule? And how do I know? This is the next game. The next game is that suppose that you are a single molecule and you receive a photon. What do you do? So the way this thing is happening is that I'm exciting you. Okay? So suppose that this excitation is I'm throwing you balls. Boom, 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 and you're throwing them back to me. So I send you a photon with my laser, you get excited, and then you de-excite. Fine. This is your de-excitation. This is your photon. I just count the photon. I throw you another one. You do the excite. I keep going. You keep giving me some signal. Okay? It fluctuates a little bit, it's flat, right? After a while, molecules get tired of all this shit. Oh, come on, I die, leave me alone. And a process called photobleaching happens. Photobleaching means that the molecule commits suicide. Harakiri, done. And it dies. So, if you keep exciting a single molecule, you will see what we call a trajectory. Light, no more light. Done, forever, dead. What is happening is photobleaching processes are complex, but it's interaction excited with oxygen. Eventually, the molecule structure gets destroyed after a while. And then, basically, you break. So, you excite enough a molecule in presence of oxygen. If there is no oxygen, it takes longer, but eventually it dies also. And then the thing gets tired of receiving so many photons. And you can imagine that as a way you are eroding the molecule structure until it dies. Now, this property, this is what we call a single molecule step. Now, suppose that you have two molecules, okay, in the sample. Now, I start to excite the two of them, and maybe the two of them respond at the same time. Of course, every molecule have a photobleaching time which is different, it's random. So now the two of them start to respond at the same time, now at the double of the height. But after a while, one of them dies, the other one follows and dies later. You see two steps. Three molecules, three steps. 1,000,000 molecules, no longer steps, an exponential decay. They start to die very quickly, and then you start to see an exponential decay. So the point is that we now need to ask our signal not only to be the right color, but to have a single step. So when I excite my sample of molecules, remember, all this is full of molecules that may give me a tiny response. But this tiny response, because there are so many of them, is dropping exponentially. While the one that is chelated is giving me a signal that after all this exponential decay will give me a step. When you see that step, and you see that is the right color, then you have the single molecule that is chelated. And now you say, okay, I have. It could. So you need to pay efficiency for that. So the thing, not a hell of efficiency because the light, the total amount of light that you have from this million of molecules is not 1,000,000 higher than this one. This one is very high compared with the million of molecules, which have a tiny signal. But I still need to have the signal of a single molecule to be sure that what I'm observing is not a conspiration of other molecules. It's a way to see it. Meaning, it's a way to see it. You don't mind that the others die. And now, of course, once this idea is formulated precisely in the way that you have formulated, it comes the question, okay, how do you precisely construct your layer? Because now there is a contradiction of requirements. I would like to put as many molecules as possible to be absolutely sure that I grab the ion. But if I make a monolayer completely dense, then I have 1,000,000 molecules per one molecule. Now, if I am going to do a dense layer, I need to ensure that the molecules, basically when they are free, they give zero response, right? This is complicated also because dense monolayers, molecules talk to each other. And so it's a mess. So the contrary situation is, okay, never mind. I put one here and one there, one per micron, then no background. Now, how are you sure that you get up there? The point is that we don't know yet the physics or the chemistry of this. When the barium ion gets close to the layer of molecules, of course, a micron distance is half of a universe. But we don't know the chemical process that is at play here. It could very well be that the barium ion keeps, according to some models, keeps going around, bouncing around, tick, 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 until it finds the molecule. So we don't know yet if the layer needs to be. So 1 nanometer apart, we know that would be perfect from the point of view of grabbing the ion, but it's impossible. Too many molecules. But once every 10 nanometers would be 100,000 molecules. Once every 100 nanometers would make 10,000 molecules, and so on and so forth. So deciding what is the pitch or the density is one problem, and designing the free molecule so that they are essentially off when they don't have is the other problem. And there's a third problem, is the substrate itself needs to be as sterile as possible. The point is that the substrate itself has atoms, quartz. And when you excite with laser, they also respond. This is why the step is giving you a tremendous handle, and the separation of response is giving you a tremendous handle, but you need to optimize all these parameters at the same time. And this is where the problem comes. So if I go to this poster that I wanted to show you, no, the other way around. The molecule is dead. Absolutely. So what? That's okay. What's the problem? How big is first of all, there is two answers to that question. But the first question is, how big is that hole? 1 micron hole. You expect that the next barium ion is going to drop in that micron hole? See, I mean, let's do the calculation, right? You have a detector. Actually, we didn't discuss that, but actually we have a detector of 2 meters. So if we would decide to scan all the 2 meters squared, the probability of falling in a given micron is 0. We actually don't do that. We actually plan to. This brings up an interesting question. How are we going to grab the ion, right? So here you have different techniques. One is I take my 2 meters squared and I put little glasses with my molecules in 2 square meters, 4 square meters. Bit too much. The other is because I know the position where the barium ion is going to get. I just make the priest goes to the mountain or the mountain goes to the priest. So what I do is the barium ion is coming, and I put my cover slip in an electric motor, goes there to the precise point and grabs it. Okay? So that would be actually this grabs it, and actually a focus with something called RF carpet, so that it goes precisely where I go. The amount of focusing that we are looking at, in the best case, would be 1 millimeter square. All right? If you compare 1 millimeter square with 1 micron square, I'm still super okay. It's actually a million holes, right? So I could burn easily. Also, how often I expect this to happen? Remember what we were talking about, 1 background event per year. So in the best of the case, I'm going to have a candidate per day, 300 holes in a million holes. It's okay. It's not a bad. But actually, it's better than that. Because it happens so rarely, I can have a pile of classes in such a way that every time that I use one, I discard it and I put another one. So actually, burning molecules is not my problem. I'm happy to burn. Okay? Everything happens at microscopic scale. All right. So this is a bit the review of the ideas. This is what we discussed it. The electrons would go here. The barium would go here. We would have time enough to open the gate and to time the gate. And then you will have your layer of green molecules. And when you grab the barium, this one goes blue. The molecules look like this. They are like, they have this little ion trap. This is what we call the crown. And they have the fluorophore part, which is the one that gives the color. And then they have a tail that allows us to put them in the surface. And this kind of stuff we have already measured. We actually, now that at macroscopic level, we had a surface on, we prepare a surface with molecules like this. Then we excited with laser and we recorded the color, and the color was green. And then we evaporated a barium salt on top of the layer and basically chelated the full layer. And then we took another picture and it was blue. So we kind of understand that the technique works microscopically, right? This was the first generation of molecules that we had at the time. This is the green part, this is the blue part. You can see the problem here is that you have a little space where you can separate one from the other. And actually, we have done really pretty interesting things with surfaces. We have taken pictures of single molecules with and without the barium. So we know for sure, using AFM. So we know for sure that we can grab barium. We know for sure that the molecule changes color. And we have also, it's not in this poster, but it's the kind of things that we are doing now, we know for sure that we can observe single steps. So this is the technique that we have been developing over the last year, is the chase of the perfect steps. We just go diluting and diluting the samples, and then we can see single step. We did last week one very interesting experiment in which we could see the steps of the molecule. So let's put it this way, the raw ingredients are all in place, right? Now, what is missing? Everything. Everything. First, we don't know yet how, first, the sensors. The sensors need to be optimized. Right now, we have some color separation. We have other type of sensors, on, off, timing, but the point is that the sensors are not fully optimized by a far call. They still overlap. There is a lot of work in the group of Fernando Cosillo, who is my partner in the Synergy grant that we have to develop all this, and who is this boss, on optimizing the sensors. So you want to push them apart as much as possible. I don't know for which family are we going now already. We call G the molecules, and 6. So this experiment there, this guy was called G1, then we did G2, and then we are probably in family G6. Every family tries a different trick. So there is a full team of chemists who do nothing else than this, optimizing the sensor themselves. Now, second problem is what is the way to produce this? One thing is the sensor, the individual sensor, and then the detector. So for that, you need to produce a layer with a given pitch at a given distance with a given orientation. Molecules, it's kind of easier to imagine the molecules like trees. They are here, oh, wait for it. But typically, if you don't think the molecules will be in any random direction. So we need to optimize, this is another chemist problem, the pitch, the orientation of the molecules. Okay? Second problem. Third problem, we need to refine the microscopy in such a way that you are able to move very quickly in your millimeter square or centimeter square and scan the whole volume that you're scanning, right? Very quickly. Well, very quickly, although not necessarily super quickly because you have forever, but you don't want to take a year for scanning this thing. So the amount of, and essentially, we need to come with experiments that allow us to convince ourselves that we are seeing a single molecule every time. Because otherwise, we are tricking ourselves. So we have a program to develop this that goes step by step. A lot of work has been developed over the last couple of years to develop sensors. Another lot of work to develop microscopy. And then the next step is launch experiments in which this goes like here. So this is what we aim to do anytime, probably, what is my pointer? Here. Next year, we want to do the first round of measurements in which we simulate the whole thing. So how we simulate the whole thing? With a barium beam. So we have expended also quite a bit of resources over the last 2 years developing a barium beam that shoots barium ions. So the experiment that we are planning for the next year is you put the target in front of the barium ions. Of course, you put many targets with different parameters, different characteristics, different this. First of all, you measure all these targets and you characterize them without the barium grab, right? And then you put one after the other, you shoot with the barium, and then you characterize them with the barium grab and try to see at which level we are able to separate one ion. So the first goal is not to see one ion. The first goal is to see steps that give me the conviction that I have ions, even shooting many of them. So the idea is that I'm going to have a layer with millions of chelated molecules, but I want to see millions of single steps. And then you keep reducing and reducing and reducing with the idea to see if you can reach this one single step. The final thing, the consideration, the most difficult consideration here was suggested already by you. I don't think that is impossible to achieve single barium detection with this technique. The pressing question is, what is the efficiency? How much you're going to pay for single molecule, for color separation, for detection, and is this single overall efficiency acceptable? Now, the concept of acceptable depends on your problem. For 10 to the 27 years, maybe it's not worth it. Maybe for 10 to 27 years, we have sufficient technology to do it, although as you have seen, it's very difficult. For 10 to the 28, maybe it's essential, because even if I am paying a big price in efficiency, it's the only way that I have to convince myself that the background level is way below. When we say background free, it never means background free. But if I am going to evaluate my background to be less than 0.1, I should be convinced with an error of maybe 0.01. And maybe it's the only way to have this kind of cross delayed single events. This is why this project, this development, is a program, we call this next bolt. Boldly going where no one has gone before, right? And bolt comes from barium tying with light detectors. Now, this is why this program is a program intended to be developed in 10 years. The synergy grant itself is 7 years, and we think on something like 10 years, not something you do in one day. But the basic ideas are there. Now, I don't want to take more time to tell you two things. First of all, your question. Can you do that in liquid xenon? You ask that. You can. Now, it becomes slightly more difficult because to all the difficulties that we have, in liquid xenon you have to grab. First of all, in liquid xenon you will have the baryon ion drifting, and there is no way you can do that with molecules. They don't work in liquid xenon. So you need to grab the ion. There are several ideas to do that. The most clever one is you know exactly as we do where the baryon is going to be within millimeter error and within millisecond. You go with a needle. You put the needle in front of the baryon, and then the baryon, together with a bit of xenon, will freeze in the tip of the needle. So the needle comes in and stays in the trajectory. A bit of xenon will freeze on the top of the needle, which will contain the baryon atom. Then you eject it in the needle, and then you have a couple of ways of detecting that. So either you evaporate from the needle the gas with a hot gas, and then you bring it to a polytrap, and you use lasers to see the baryon signal. This is very well known. The baryon signal in a polytrap by resonant laser excitation is kind of very easy. It was developed 40 years ago. You just leave in a polytrap the baryon there among magnetic field, you keep exciting it and it gives you signal. But this is, in a way, one more step of complication than the next, because you need to grab, take, and bring. Okay? The program is there, and there is also a group of people in Nexo working on that. And in their case, I think they even take it as an even longer project than we do, because they say, okay, first I will do all the physics I can do with my 5-ton detector, blah, blah, and then I will think about that. But at least on paper, you can do in both detectors the same thing, okay? With very different techniques, though. And that was basically what I wanted to tell you today. For the solution of your research projects, I will post GitHub place where you can find the solution, and I will send it to the school so that you can, after the school, you can check the solution. And you will see that the calculation that I propose shows that you can control, under the conditions that I propose, the bismuth 214 very well. And then you can ask yourself the reverse question. How much bismuth 14 in total I can tolerate before I cannot control it? Okay, so that is what I had to say for today. Thank you very much. It has been a pleasure to teach you. Yes, this is an important point actually, and one that I didn't stress much, but is great fun. This project requires to talk to chemists, which is the most similar thing you ever imagine to an alien civilization. You really need to get there and start by talking to chemists. You start to make signs so that you develop a common language. Alien civilizations, they're very nice people, but everything that you think means something different from them. So already talking to chemists is an elevation of the spirit. But then you need to do high top microscopy. We need to do quite a bit of precision electronics. So it's a completely brave new world for us, and it's part of what makes this thing quite a bit of fun. I did my best, but I typically fail. But I typically fail. I don't know why, but I typically fail. Thank you very much, everyone.